Welcome to the Hackaday Remoticon. It's so great to have you all here. My name is Mike Stish. I am editor-in-chief of Hackaday.
I'm Sophie Kravitz. I'm director of product at SupplyFrame. I am in New York State, and it's kind of cold outside and a little bit sunny. So I'm on East Coast time. There's been a lot of conversation about time zones today. Mike?
Yeah, so I'm working on how to figure out how to go back and forth between different spotlightings. You might need to choose the speaker, Sophie. We're really excited to have everyone here. As with all online events that are happening these days, please bear with us if we have any audio and video difficulties, but so far things have been going great. We had a wonderful Bring a Hack last night on a new platform that we haven't used before called Remo, which was a ton of fun. And Sophie has agreed to open up another one of those today at 5 p.m. Eastern time. I think that's 2 hours earlier than yesterday. So hopefully more of our European friends can participate in that and have it not be quite so much in the middle of the night. But that was a great platform. I had a ton of fun over there.
Yeah, well, for the rest of today, we're going to have workshops going until 6:30 p.m. That's Eastern time. And then we want you all to join us back here on Hackaday's YouTube channel for Alfred Jones's keynote. And he's going to be talking about designing hardware for self-driving cars. Let me put you back, Mike.
After that, we'll be announcing the winner of the Hackaday Prize. The 2020 Hackaday Prize started all the way back in the spring. We had hundreds of entries come in, and it's going to be very exciting to see not just who won the grand prize this year, but to see who won the best in category and the runner-up prizes for each of our nonprofit partners. There were 4 of those nonprofits this year, and to see the wild card winner. That is really exciting to see, and that will be, like Sophie said, right after Alfred Jones's keynote this evening.
So we've had a lot of questions about where the schedule is for this event, and I think that this is our 7th year of doing an annual November event, and as usual, our schedule is in a bunch of different places and a bunch of different time zones. And if we didn't do it like that, it wouldn't be Hackaday's Remoticon or Hackaday's Supercon or a Hackaday event, because time zones are hard. It's really hard to plus and minus by 3, by 12 Eastern time, Pacific time. So the main schedule is on the online Eventbrite page. So if you have a ticket, whether or not you signed up for workshops, that's where all your passwords and links to everything will be. We also have a wayfinder for all of the workshop chat rooms, and that is at remoticon.io. And that has a special musical surprise. You can enter demo into the bar below, and there's something really cool there. If you want to get in touch with us, we're using the email superconference@hackaday.io. And I think that's all I've got. Mike, do we have anything else?
I don't think so. I think we covered it all.
Okay, and with that being said, we're going to kick off our first keynote. So our first keynote speaker, Kipp Bradford, is an engineering researcher and the CTO of Treau, a startup which develops high-efficiency heat pump systems. Before that, he was a research scientist and faculty at the Yale University School of Architecture. He worked for several years at the MIT Media Lab as a senior research scientist. He was hired, he told me the story about being hired as a result of a faculty search for the professor of other, which is an interdisciplinary scientist. His research is extremely relevant right now, merging biology, ecology, and thermodynamics to develop new ways to manage climates at every scale, from personal thermal comfort up to global weather systems. He is the founder of Revolution by Design, which is a not-for-profit education and research organization which is dedicated to the empowerment through technology, and of the Innovation Institute, an NSF-funded project that taught technology innovation to unserved youth in New York City. Kipp joins us today to discuss how the things we make, the things that we engineer, impact the lives of people and have effects that ripple through society. Hackaday was extremely honored to have Kipp as a Hackaday Prize judge in 2017 and 2018, and I am really honored to introduce him here today. Please join me in welcoming Kipp Bradford to the virtual Remoticon stage.
There we go.
Okay, let us
Thank you. It is great to be here. Looks like lighting is working and everything. And I will have a few slides to share that I'll pull in as we get to it. But I want to get started. I'll start with a couple slides. Yeah. Let's see. Mouse is moving a little slowly here. So my mouse has disappeared. There we go. Uh-oh. Screen sharing has failed to start. Please try again later. I don't know if the permissions are set. I meant to do this.
This is probably my fault. I probably have it set so you can't do that. Let me go to security and there you go.
Let's see. It looks like, okay, great.
Yeah.
All right. So screen sharing is paused. Let me just try that again. All right. Looks like this is working now. Good. Okay. I thought I would start with a silly and slightly fun little slide. This is one of my very, very first projects out of college about 25 years ago, which was a doll, as you can see here, with a 4-bit microcontroller programmed in assembly that for a biomedical engineer was quite a project, quite a lift. It had a little switch mechanism in the hand, and the switch mechanism was built on some Legos where I drilled out the studs and used that as a 3-bit binary encoding system that would allow me to detect different types of accoutrements that were put in the doll's hand, and the doll would respond to the different things with different actions. So here's a rattle. When you put the rattle in the hand, the doll would shake the rattle and would make some sounds. If you put a teddy bear in the hand, the doll would take the teddy bear up to its mouth, give it a kiss, and make some other sounds. If you put a pacifier in the hand, it could detect the pacifier and then put the pacifier in its mouth. So this was an interesting exercise for me because it represented engineering meets humans in a strange way. After 4 years of undergraduate and then some time in graduate school, I realized that I'd been working kind of in a physics vacuum, and that physics vacuum was really looking at how to implement different kinds of physical systems, how to build various technologies. And this was the first time that I'd really put the pieces together with the fact that everything I build is going to impact a human being in some way. And in the sense of being a biomedical engineer, it was kind of a shock to me that after 5 years of school, I hadn't really thought about the human that I was engineering for. And it really took this job where I became a toy inventor for a few years to look and say, wow, I'm going to engineer things that have an impact on people's lives. And in this case, a very small impact. It's a toy. But when I took a step back and thought about the broader scope of the toy work that I was doing, there's a lot of stuff that we were creating that would end up in landfills. We were working as toy inventors where we were licensing ideas. The things that we would create would typically be played with a kid for a couple days, a couple weeks before they got bored. And then the kid would want the next thing. And that was almost a design decision, because if you think about what these toy companies were after, they're not trying to get kids to be creative and use their own imagination and play with something for years on end. They're trying to get something that a kid's going to look at and say, I really, really, really want that, and get their parents to buy it. And after some period of time, we would see the toy companies wanting the kids to buy the next thing because that generates revenue for them. So this put a lot of things in perspective for me, despite the form factor of the project and how kind of weirdly disturbing it is. It really brought engineering into a context that I hadn't been exposed to before. And that's a little bit of what I want to talk about today. And my slides are a little bit scattered, so excuse that. I got distracted by the events of the last week. So the first thing I want to mention is that technology is not neutral. And let me just see, I need to pull up my notes here. Let's see if I can switch back. Sorry, not quite got my setup. All right, well, we'll just continue on. So technology is not neutral, and I do need to actually read my notes for this one. So I want to bring up Melvin Cranberg's laws of technology and focus on a couple of them. Technology is neither good nor bad, nor is it neutral. Invention is the mother of necessity, not necessity is the mother of invention. Technology comes in packages, big and small. Although technology might be a prime element in many public issues, non-technical factors take precedence in technology policy decisions. All history is relevant, but the history of technology is the most relevant, and technology is a very human activity. So is the history of technology. So these are some pretty important comments. You might agree or disagree with Melvin Cranberg. I happen to agree with him, but I think I want to highlight a couple issues and ideas related to this. And let me see if I can do this again. So I can't see my notes if I am doing this for some reason, but we'll just wing it a little bit. What fundamentally separates us from other animals is that our intelligence allows us not just to reshape our landscape like ants making an anthill, but also we can fundamentally understand how nature works and use that understanding of nature to change the world around us. We can overcome our natural and physical limitations through technology and engineering. What that comes down to is that human beings have very special powers. And to me, those special powers are manifest through engineers and how we as technologists make choices about the things that we make. One of the, Sorry about jumping around a little bit here. One of the things that I think is an important observation about this is that we as human beings augment ourselves and our environment, and those augmentations become part of humans as a species. Our technology evolves as we do, and it evolves us. This is an idea that I'm sure other people have had, but something I've been thinking about a lot that I have been pushing on, which is the idea that technology is part of human evolution, and the things that we create and the augmentations that we build around us are things that are passed down not as part of our physical DNA, but they're sort of extracorporeal DNA. What I mean by that is that, for example, if it's hot out, over centuries, we might expect to see adaptations for human beings physically, where we sweat more effectively, where as we breathe, we exchange more heat through the air in our lungs, and we become better adapted to survive in these high temperature environments. So that's biological adaptation in its classic sense. But humans have this very interesting and very new form of adaptation, which is technological adaptation. In those same environments, instead of having our DNA be nudged in one direction through selective processes, we can actually understand nature, understand that we can cool ourselves actively in these environments by applying energy in a certain way. And we document that information in the form of patents, in the more recently in open source and Wikipedia articles, instructions on how to build things. And that's something that never goes away. You can't take that away from us. That's passed down from person to person, from generation to generation, in this larger schema of knowledge and information that's carried forward. And that larger schema is what I call this external DNA, the extracorporeal DNA, because it's instructions for how we can build augmentations to the human organism, an augmentation that makes us be able to, for example, teleconference over the internet, or keep ourselves warm, keep ourselves cool, defeat a virus. Our own immune system might not have the right signals, say, to defeat coronavirus, but we can do a ton of research, build that information into vaccines, into treatments, and then that knowledge is passed on from generation to generation. So we've effectively evolved the organism on a time scale that is unprecedented compared to biological time scales. Another important factor about this is that good ideas reproduce and they're passed on. Hopefully bad ideas die off. We also have to think about what it looks like when those ideas meet the broader forces in society. And to expand on this idea that technology cannot be neutral, I am quoting a research article from Lance Straight in Technology Journal, who said that taking a media ecology approach, technology cannot be neutral because it is a form of change. It has an inherent bias based on the properties of its materials and methods. Additionally, the application of technology is an intrinsic part of technology itself, as is technique, instruction, software, or know-how. Moreover, the bias of technology cannot be reduced to the designer's intent, as innovations always have unanticipated, unwanted, and undesirable effects. I think these words are profound, and it really captures what I'm talking about today. This idea that we sit, I'm in my basement right now, my inspection scope, my oscilloscope, my lathe, I've got, let's see, which way do I slide here? Some CNC circuit board making materials right behind me. In my garage that's over that way, I've got a brazing rig that I can use to make air conditioners, heat pumps, things like that. So I'm fairly well equipped to be able to make things that hopefully and potentially have impact on people's lives, which I'll get into a little bit. Encapsulating that power and understanding that power, I think, is something that cannot be ignored and should not be ignored. And all too often, we as engineers and designers, we want to ignore it. We want to think about not the impact that we might have on society, but we want to think about the thing that we're building. And there's nothing wrong with that. I think that that's why we do the work that we do. I also think that it is important to put this work into this broader context. So I'm going to transition a little bit and kind of go through some of the story here, and maybe without transitioning back and forth to slides. 2020 is an extraordinary year. I don't think it's an overstatement to say that. I do want to reflect on some of the positive technological achievements that have happened in 2020. I'm blown away by the fact that we have the Osiris-Rex Probe. I know that these first two things are going to focus on space, but we sent a probe into outer space, landed it basically for a moment on an asteroid, collected a large amount of sample material, somewhat securely put it back into a sample storage container, and are flying that back to Earth. That's super cool. The amount of amazing achievement that went into making that possible can't be understated. I mean, just trying to land this thing on a rocky body that couldn't be inspected. You know, we couldn't look like we did with the moon and say, where are the craters? Where are the flat spots? Where are the things that we need to watch out for? We haven't sent multiple probes to Bennu to see where the optimal landing spots were. All of that was figured out using some grainy images, launching a rocket with enough smarts to be able to get there safely, do its job, and then come back. That's can't be understated. We've also launched people into space safely on a new rocket, and I think that's another achievement that can't or shouldn't be ignored. Going back to the other items on my list that I do have some slides for. Yep, move that out of the way. Let's see. So I started the year by going to CES, and at CES, there's a lot of excitement about blockchain technologies, a lot of excitement about Internet of Things, as always is the case, a lot of excitement about energy technologies. 5G was all the rage. Television screens that were the size of the wall on a medium-sized house, things that just represent the amazing power of engineering and science to make just hard to imagine things even 5 years ago. The power of artificial intelligence and machine learning and the applications that are working. You know, we look at things like self-driving cars being hard, but and say, oh, maybe we haven't quite gotten there with some of the technology that is underlying artificial intelligence and machine learning. But at the same time, there's some massive wins with machine learning. I was talking with one of the heads of the DeepMind project at Google, who was saying that they ran their tools on a server farm and were able to optimize a control system that had millions of variables in it. And through that machine learning optimization, they were able to get a 40% savings in energy consumption. And they published a great article on it. That sort of work, where we're getting massive wins through computation, through better approaches to problem solving, technical problem solving, those are things that we have to celebrate, and we have to respect the advances that we're getting there. There's also been a lot of hyped tech. When I say 5G, there's both the opportunity and also the reality. But all of that said, I think we also have to recognize that it has been a bizarre, a sad, and a momentous year. Right after going to CES, the next conference and last conference I went to this year was one called AHR, the largest, it's the heating, refrigeration, air conditioning trade show, largest in the world, 100,000 plus people, probably another hotspot for spreading pandemic. But one of the observations that I always make there is that there's a lot of really old technology that uses tremendous amounts of energy that sees very, very little innovation. And it's not an exciting field to work in. I've talked about it at Hackaday before, but it's one that has massive amounts of importance to the world. So that transitioned me from all of the hype and excitement of CES to the reality of, wow, you know, there's a lot of work to do to make the world the place that we want to live in. And then leaving AHR and facing the full brunt of global pandemic, we're seeing over 100,000 people getting infected per day in the US. Hundreds of thousands of people in the US have died. We can't underestimate the power of these things to drive change in society, from bad change, like people repudiating science because it interferes with their desires for freedom, to good change, things like the open source personal protective equipment projects and people coming together to help healthcare workers work in better, safer environments. We look at the Black Lives Matter protests this year, and Rhode Island just voted finally in 2020 to remove the word plantations from the state name. You know, these throwbacks to a day where slavery was the norm. And it's 2020 when we're looking and saying, maybe this isn't the thing that we want to reflect in our society. I think understanding today that the world is in an interesting place. You might call it turmoil, you might call it more of the same, whatever your stance on things, it's maybe most important to recognize that technology changes things. And there are a lot of simultaneous existential threats to civil society that we see today. There's climate change, there's a global pandemic, rising authoritarianism, there's a lot of financial inequality. Some of you might be nodding your heads in agreement with me, and some of you might be saying, what the heck is he talking about? And you know what? I get that. I respect that, because I understand that we're not all impacted by the same things in the same way. We might see these challenges in a different context. We might not see these challenges at all. And if you don't see these challenges, or you see them in a different light, it might be easy then to think that they're not problems, they're not global challenges. But the thing that I urge you to do is remember that just because things are going well for you or going well for us, and the system is working for you or is working for us, there are a lot of people out there for whom things aren't going well and for whom the system is not working. And I also respect the fact, and I think that this is the right thing, that there are no laws saying that we have to work towards a better world. And there probably shouldn't be laws forcing people to work towards a better world, because we don't know what the better world is. We can only look back and say that things got better for us or they didn't. And I take us back to the words of Lance Straight, which is that technology is a form of change. So what does it mean to look into the future and understand the world that we want, and try to get there with technology? I think I tend to be a techno-optimist, that technology can cure all these problems. And I see the sticking point as politics. And I don't say that in a way that politics is wrong or bad. I say that in the light that politics is part of society. It's a part of the decision-making process in society. One of my classmates in college said, I don't believe in politics. I don't think that politics should ever be part of engineering. And I've heard lots of engineer colleagues say that, like, I don't want to deal with politics. I don't think that politics should inform what I do as an engineer. Um, I it's always interesting for me to hear people say that, because if especially the friend who was a civil engineer who said that to me, and I think that the insight here is that, like I said, politics is really the decision-making process of a society in a lot of ways. And one example of how that impacts technology, I think we all can reflect on this very moment. Imagine a world where every eligible voter in the United States could vote digitally, and that vote could be registered instantaneously. So instead of waiting a week for the results of an election, we can know within a matter of minutes or hours, without people having to go to polling booths, without anyone ever having to leave their house. What would that world look like? There are a lot of questions that we'd have to ask there. How do you maintain privacy? How do we ensure that every registered voter has access to a voting portal, whether it be a computer, a phone, or a voting booth? How do you properly vet identities to make sure that there is no voter fraud? How's the integrity of the data maintained from end to end? How do we make sure that there's no hacking? I would argue, and lots of people have argued this, that we've solved these problems technically. We have blockchain, we have the means for biometric identification. All of these questions have a technical solution. But we have not merged those solutions with the political will and political motivation to implement those solutions. There's a decision process that has looked at this body of technology that people like us have created and said, that's not what we want to do today. That's not what our society wants to move forward with, for whatever reason. I won't get into the reasons. There's lots of theory about why some people don't want more people to vote or have access to voting, and why some people do. But what I will reflect on is that after the 2016 election hacking scandals, a lot of jurisdictions actually went back to paper voting so that they would literally have a paper trail for the votes that people made, instead of digital, where they thought, you know, those digits could just evaporate. Like, what happens if the bits get flipped? Cosmic rays hit it, or somebody hacks the box. If we have paper, Russian hackers can't access that paper. So that was the thinking, that paper brings confidence. All the newfangled fancy technology that us technologists make, that's all great. I don't understand how it works. I understand how paper works. I can touch paper, I can feel it. It is tangible to me. I call this the Firth of Forth Bridge effect. And if you look up the history of the Firth of Forth Bridge, it was built after the Tay Bridge disaster. And one of the design criteria was that the design of this bridge must instill confidence in the structural integrity of the bridge. This was not an engineering edict. It was not that you have to maintain a certain load profile across the members of the bridge or the structure of the bridge. It was not that we want to optimize for certain material strength and cost. It was that there must be public confidence. When they look at the bridge, they say, that looks like something that I want to cross. So there's this profound interaction between the engineering and the societal impact. Another thought and observation about this politics engineering intersection is the story of the light bulb, and not the Edison Swan light bulb. Hopefully you all know who Joseph Swan was. But thinking more about the modern light bulb. In 2011, going back to my slides here, in 2011 and 2012, there was a law passed that was going to phase out the incandescent light bulb by 2012. And that law was actually pushed by George W. Bush, trying to make efficiency the norm. But it also had an interesting underpinning, which was that American innovation and American industry in 2010, 2011, 2012 had been pushing white LEDs, which came out of a lot of research in universities in the US and in Japan. And US companies were taking the lead on manufacturing high efficiency white light bulbs. But there was a pushback in Congress that said, we're going to undo this ban, which is driving people forward to using white LEDs and driving these industries in the US. We're going to undo that ban, and the markets will decide what will win. That was great, unless you were a US manufacturer of white LED light bulbs, where those regulations were opening up a new market. Unfortunately, China said, hey, that was a smart idea. We think that there's going to be a shift. We're going to drive this market in China and support companies to basically take the innovations from the US researchers. We're going to commercialize them. And now all the light bulbs in my house are LEDs, white LEDs that are manufactured in China. So there's a missed opportunity there. If you think about the decisions, the political decisions that the American political infrastructure made, with the longer term implications being that there's a market opportunity that shifted from the US to China. So that also, there's a conversation I had with a senior executive at one of the large HVAC companies who said, the only thing that pushes my industry is regulation, which becomes a really interesting challenge, because we have lots of opportunities to create new markets, new technologies that work in those markets. But the gap between implementing those, I can't tell you who said that because it was said in confidence in a private conversation, but I will tell you, as a senior executive at one of the largest global manufacturers of HVAC equipment, you could probably guess which one of the three it is, but like I said, I won't out this person publicly. But the implication is that in some senses market forces work, and in some senses market forces interact with technology, and they interact with the politics and the political will and the political direction of governments. And I think we all need to take a step back and understand that. I want to quickly, since I'm running out of time and I would love to talk for another 2 hours about this, want to quickly reflect on a couple takeaways and then some projects. So for me, the message here is that we have to, as engineers, designers, technologists, hackers, makers, we have to put our work in context. It's important to focus on your work when you're doing it and think about the beauty of technology and the beauty of science and the beauty of engineering. It's also important to understand that broader context and to think about how we want our technology to be used in the world. What do we want that impact to be? What do we want the world to look like 5 years from now when we bring our work to life? For me, I spend a lot of time in my garage brazing. If you search for the tested video I did with Adam Savage, this is a really fun project where I was working on a wearable air conditioner for him. He's a fantastic guy. He's a great person to work with, good friend, and it was a lot of fun. It also is part of work that I do looking at how we use less energy to make people comfortable with heating and cooling, which is one of the biggest consumers of energy and one of the biggest producers of climate change emissions. And another project I did with some colleagues at Princeton University called Cold Tube, where we were looking at how do you cool people in environments that are hot and humid and do that with less energy. The team at the Chaos Lab, Forrest Meggers, Eric Teitelbaum, and some collaborators, Adam Rysanek and others, were super creative. We made something that could cool below the dew point without creating dew and humidity and condensation. humidity is there, but without condensing the humidity in the air, and that's an interesting problem to overcome when you're trying to cool people in Singapore and use less energy. Another great project for you to look up is the ELM, E-L-M, the Ecological Living Module that I worked on with colleagues at Yale University, the Yale School of Architecture, in collaboration with the United Nations, that's looking at the future of disaster relief housing and the future of refugee housing, how that can be made sustainably in large volume, large scale. Those are a couple cool projects, and I really should close with this question of how does your work impact the world, and what do you want that impact to be? And be thoughtful about that. We, as engineers, are told that we have to take ethics classes. I think that's a failure of engineering education. We should all be ethical humans. We should all be humanists, because engineering is human. I know I'm running out of time, so I just want to very quickly give a few shout outs. First of all, to all of you for being here. Thank you. Thank you for putting up with some of the technical difficulties. Sorry, my slides are great, but you didn't get to see them. Maybe another day. Thank you to the Hackaday team, Sophie, Christina, Mike, everyone who's helped put this together and bring this community together. I should definitely give a shout out to some organizations that I'm involved with who are, I think, doing really powerful things in the world, doing great things in the US to support engineers and makers and to try to make the world a better place. The Maker Education Initiative, Nation of Makers, the Beagleboard Foundation, Kyle Cornforth at Maker Education Initiative is amazing. Dorothy Jones-Davis at Nation of Makers, Jason Kreidner, who many of you know at Beagleboard Foundation, the rest of the board of directors. And, you know, I will say that there's a lot of parts of government that are working really, really well with engineers and scientists to try to unlock the potential of human beings. And in California, the California Energy Commission is a surprisingly innovative and thoughtful and forward-thinking branch of California government, as is the California Strategic Growth Council. They fund a lot of projects trying to basically make people's lives better, but doing it in a way that supports industry and supports commercial efforts. US Department of Energy, National Science Foundation, Hackaday obviously is a fantastic organization, and the Open Source Hardware Association is dear to my heart as well. So with that, I'll leave you with one thought: don't build bridges in the middle of the ocean. Technology in and of itself is great, but the bridge has to connect two pieces of land to be useful to humans. And if it's not useful to humans, it doesn't matter. So don't build your bridges in the middle of the ocean. Put them in places that make a difference. Remember that technology extends the DNA of humans. Some of that can cause cancer. Some of that can cure cancer. We want technology to extend DNA in ways that cure cancer. And to close with the title of a book from Henry Petrosky, To Engineer is Human. So think about the human impacts of engineering. I'll leave it there, and hopefully me ranting from my basement somewhere in New England was interesting to all of you. Thank you.
That was awesome. Thank you, Kipp. It's also really nice to see you again. And, you know, now we're in our shops, which is also kind of different and cool. I think the last time I saw you was in January when we were still allowed out.
Yes, so. I'd love to give you a tour of my shop, but then you'd kind of see my laundry room and, you know, lots of cool circuit boards down here that I can show off. I've got my surface mount equipment next to me. Like I said, my mechanical equipment is here. There's when you're in the Northeast, you know, states like Rhode Island, real estate's a little bit cheaper than say in San Francisco, so it's a good place to be.
Yeah, yeah, especially if you're doing stuff that is mechanical and requires a lot of big tools.
Yeah, having a garage where I can braze stuff and build heat pumps. The largest heat pump I built is about the size of a small refrigerator. The smallest heat pump I built was one that fits in a wearable air conditioner for a backpack for NASA. The one that I built for Adam Savage is a little bit bigger than the NASA simulation heat pump, but having a little bit of space can help. If I was doing electronics, it wouldn't matter.
So we're going to do a quick Q&A, and I took a few questions from our chat. We've also got a fair amount of compliments over on YouTube. Don't go there yet. Let's do a couple questions.
Let's do the questions.
Okay. So well, I'll do an easy one. Have you read any good books lately? What do you recommend?
Unfortunately, I haven't really read much this year that's not been research papers, thermodynamic textbooks, power electronics textbooks. So I've really been heads down in research and startup land, trying to do a lot of thermal optimization. So if you have recommendations, last time I hung out with Mike, we exchanged podcasts. I've been listening to a lot of podcasts and a lot of radio, a lot of new music, but I'm looking forward to taking a little bit of rest from work and reading. I've been working 60, 70, 80-hour weeks for the last couple of years. Not totally great, but riding a bicycle a lot.
I know I was going to say that since you're in Rhode Island, you have room for brazing equipment and bicycles and electronics and heat pumps and and laundry, all in the same space.
Yeah, and people, friends out there, Rhode Island's fantastic. If you're interested in coming to move to Rhode Island, hit me up. I'll give you the tour, tell you what's what. We have some great maker spaces, great universities. There's beaches, shore, there are mountains up a few hours away.
It's just a little cold, that's all.
It's 74 degrees out right now.
Okay, that's just today.
In November.
That's just today, climate change.
Yeah.
All right, I have 2 more questions for you, and then we'll say goodbye, and people, you'll give us a way to contact you.
Yes.
Yeah, make sure you don't forget to do that. So next question is from Anil Patney. And he asks, what can the current political system and voting processes learn from open source culture?
Oh, that's a great question. I hate to say it, but I have to turn that question on its head, which is what can open source culture learn from political processes? And the reason I do that is that I think the sticking point here is really not the open source community, and it's really not the technology. I think the technology is there. The technology exists. The question to me really is, why is it that we have these great technologies that don't get implemented? What's keeping the solutions that we know exist and that we know work? What's keeping those solutions from being put out in the world? And some of that really is when you listen to the news, the real news and the so-called fake news, there's just a lot of history and a lot of lack of desire in some ways for enfranchisement. I mean, you look at the history of the US, and women having the vote is not a historical thing. Ex-slaves, African Americans having voting rights, these are new things, relatively speaking. And I think that that's something that we have to take a look at and say, maybe it's not in everybody's best interest politically for every single eligible citizen in America to have access to the vote. And that's the thing to me that has to be overcome in order for those technologies to become desirable by the people who have the power to implement them. And that's really the work that engineers have to do, is to step back and say, I've made this thing that could have an impact on society. What's preventing that impact from being realized? And how do I then go and work to advocate to move these things forward? What are the pathways? What are the venues? That's unfortunately really the second job that we all have. We have to advocate for the things that we do. We have to educate people for them to help them understand what the benefits are to them, to society in general. And for some people, it might not be beneficial for everyone to have the vote. During the Clinton election, I saw firsthand one of the companies that was the major contributor to both the Democratic and Republican presidential campaigns, hosting politicians in the Carnegie Deli in New York City, where anyone could walk in and just get whatever they wanted for free for a week. And they were wining and dining politicians because they wanted to make sure that their voice was heard more than other people's voices. And that's the reality of our open democratic society. We have to recognize that reality and understand how that plays out and how that might be threatened by, individuals being able to vote very, very easily. So those are the sorts of things where looking at the impact of the technology on politics, the impact of politics on technology, why successful technologies don't get implemented, or functional technologies don't get implemented, and what those barriers are.
Awesome. So you actually just answered somebody else's question in that whole thing. Can you tell our audience how they can get in touch with you? And
yes.
Say goodbye. And I would encourage you to go to the YouTube channel, and maybe if you want to look in the chat, there's a lot of really nice words for you. And probably questions too.
I've been totally silent on social media for the past few months as I've been navigating, trying to keep a startup healthy and keep a toddler healthy and keep myself healthy. But I'm going to use this as the catalyst to be more active on Twitter. So I'm at KippWorks on Twitter, which is KIPPWORKS. I know some of you already follow me, and I'll try to be a bit more responsive. It's probably the best way. And maybe I should also I'm on Instagram also at KippWorks. I'll try to be a little bit more vocal in public. I'm also going to be hosting a panel or a panelist at a Department of Energy panel in 2 weeks. And happy to continue the conversation there. And also happy to, through Hackaday's platform, have just like office hours to continue the conversation. And Sophie, we can talk more about setting that up. And because that's probably the best way, because it's everyone in the same room and just having a conversation. Those are great things. I would love to be there in person and meet people and get to interact, but Twitter right now is probably the best way.
Yeah, we would love to have you come and do an office hours, talk to us about energy, thermodynamics, all that kind of stuff that you've been working on for as long as I've known you.
Yeah, I also, a lot of people have said thermodynamics was the thing that they hated in college and as engineers. And I love thermodynamics, but I hated my class. It's really taken 25 years for me to get to a point where I feel like I have a deep understanding, at least of the thermal systems that I work on. A deep understanding meaning that I understand the things that I don't know and where to look up answers and who to talk to. But it's a super exciting subject for me because it's where electrical engineering, mechanical engineering, materials science, and in terms of like air conditioning, biological systems, all of the fields of engineering to me come together in thermodynamics. So it's been just a super, I hate to say the word, super cool area to work in. And I'm excited to talk about it and answer questions about how these things work and why you should use vapor compression instead of thermoelectrics for most of your things, except for the things that thermoelectrics work better at.
Well, thanks. Thank you for being with us. I want to use that word, that you are super cool, Kipp.
Thank you all again. Thank you, Sophie. Thank you, Christina and Mike. And thank you everyone for joining in and bearing with all the slides that I didn't get to show. So I appreciate it, and enjoy the conference and look forward to meeting you all in person one day. This is the transitional dead air.
Yeah, I'm not sure what's going on here.